Let's go ahead and get into section 4.8, which is about analyzing graphs of polynomial functions. And so 4.8, we're going to continue off where we left off at 4.6 is being able to graph our functions. And remember, when we're graphing, we do need to understand based on the polynomial or the degree of the polynomial, whether the function is like the end behaviors, whether it's going to go up, both sides down, one up, one down, based on the power being even or odd. We could figure out where the function is going to intersect the x-intercept based on if it's a repeated solution or not. So kind of using those ideas, we're going to be able to graph functions, some more, and then we'll talk about a few other things. For example, local maximum, local minimum, coming right up. Now, as we go ahead and scroll down right here, we have in our core concepts, they say zeros, factors, solutions, and intercepts. Well, in the end, all of this stuff, it means the same thing, kind of. We're finding the same exact thing. Remember, when I said what they're saying is if we have a polynomial function, okay, and it says, let's say the polynomial function was, they give you this long thing right here, but I can go ahead and just say f of x is equal to x squared plus 2x plus 1. And I could say find the zeros. Well, remember, the zeros are the same thing as the x-intercepts, right? If I take the function, I set it equal to 0, well, you could either factor it, okay, and you could find what k is. You could use the quadratic formula. So there's several different ways that you could solve this problem out. And once again, they all mean the same thing. If you want to find the x-intercepts, those are your zeros. If you factor and then solve it and set it equal to 0, then you're figuring out, once again, your zeros. So these four terms, they're used interchangeably, and they are all finding the same thing, which is this value of k right here, according to, that's the variable that's used in the example. Right? Each of these has k, and that's what you are essentially solving for, which could be a 0, a factor of the polynomial, a solution, or your x-intercepts. All right. We're going to talk about turning points of a polynomial next. It says the graph of every polynomial function of degree n has at most n minus 1 turning points. Let's go back to our trusty and faithful parabola. Y equals x squared. So let's see. Let's use this right here. If I have y is equal to x squared, the degree of the polynomial is 2. Well, what they're saying is that if you take 2 and you subtract 1, you're going to be left with the amount of turning points. And this one means we have 1 turning point. And isn't that a true statement? Because if I were to graph this right here, lo and behold, there's my parent function, and there's 1 turning point. That's where the function actually turns. It reaches its maximum or minimum, and then it changes directions. So if I have right here, now it says at most, because it's not always going to be true. Let's take a look right here. If I have y is equal to x to the third, well, remember this function from earlier in the school year, it looks something like this. And there really are no turning points. Okay? So that's why it says it has at most. Right? It doesn't tell you that there will be, like for example on this one, 2 turning points. Because there are not right here in this example of y is equal to x to the third. So keep that in mind as we kind of go about the problems. So let me draw another function right here at this bottom part, since I already have this pre-made. It's there for a reason. Let's say I have a function like this. We have two turning points, one right there and one right over here. Those red dots, turning points. So technically, it could be y is equal to x to the third. Well, what will happen is that it'll be y is equal to like x to the third plus 2x plus 5 or something like that. So it'll be a little more complex in the function, but right here, because there are two turning points, it could be y is equal to x to the third. It could be. Is it? Most likely not. It's going to be probably y is equal to x to the fifth plus we continue on with our polynomial, like y is equal to x to the fifth plus like x to the fourth plus 3x to the third, so on right there. That's what the function will look like. The next part says if a polynomial has n distinct real zeros, then its graph has exactly n minus 1 turning points. So if I were to give you, like, let's say right here, in this example, are there any distinct zeros? I know it's not factorable, so most likely it doesn't look like there are any distinct zeros. I can't solve it and get nice numbers as a zero. But let's take a look at this one right here. Once again, our good old faithful y is equal to x squared. Well, do I have distinct zero? If I take x squared and set it equals 0, I go ahead and square root both sides. X is equal to plus or minus 0 or just 0 itself. You see how this is a distinct 0. It's 0, a nice number, a whole number. Well, we have exactly one turning point because we take 2 minus 1. So if it's factorable, you're going to see that there is going to be some distinct zeros and there will be exactly one turning point. So in some of the problems that we've gone over throughout this chapter, if it was completely factorable and it was really nice, then you had exact number of turning points because of the number of zeros we have. All right, and once I kind of added this right here, a turning point is where the function changes directions. All right. We have here, we're talking about even and odd functions. What exactly does that mean? Well, let's take a look. A function f is an even function when f of negative x is equal to f of x for all x in its domain. The graph of an even function is symmetric about the y-axis. So remember, we take a look at our diagram right here for an even function. Here's our y-axis, and if I were to fold the paper or fold my function over that y-axis, it will overlap each other. And it looks like it will right there. What you're going to have to do, however, is you're going to have to test this out. And the test here is this. If you plug in negative x into your function, and if it remains the same, then it's going to be considered an even function. Okay? I'll talk more about that in a bit. Let's take a look right here at the next one. Well, how do I know it's an odd function? Well, if you take f of negative x and you substitute that in to the domain or all values of x, and when you simplify it, the signs of your functions are all opposite, then it will be considered an odd function. And the graph of an odd function is symmetric about the origin. One way to recognize a graph that is symmetric about the origin is that it looks the same after you turn 180-degree rotation around the origin. So if I take this right here, and they're saying if I turn it 180 degrees, I know that this is an odd function because it looks exactly the same. If you look right there at the diagram that's shown, if you were to take that and turn it, or as we would say, rotate it 180, it will look exactly the same as what you see there. So let's add a few things to your notes to help you understand what I just talked about. So in order for us to test without actually graphing to see if a function is even or odd, here's what we're going to do. We're going to replace x with negative x in our equation. So it says if f of negative x is equal to f of x, meaning the equation stays the same, then the function is even. So you're going to plug in negative x into your long function, wherever x is. If it looks like the original function, it's even. However, if you plug in negative x into the function and all of the terms in the function are opposite, then the function is going to be considered odd. I've got three equations right here, and we're going to test that out. We're going to figure out in these three examples whether it's even or odd functions. So what they're saying first, we have f of x is equal to negative x squared plus 5. I'm going to go ahead and substitute everything, all my domain, which is all values of x, with negative x right here. So I've got negative, and I'll put negative x right here to the second power plus 5. Order of operations is once again important in this section, or else you may not get the problems correct. So let's simplify this right here, and I got negative x squared. That's going to get me x to the second power. But there's this negative out in front. So it's going to be negative x squared is what it simplifies down to plus 5. Guess what? These two are the same, right? So if they're the same, what does that tell us? We have ourselves an even function. Let's take a look at the second example. So we have f of negative x. We'll plug in negative x for my domain. And we got to simplify this out. We start off right here. Negative x to the fourth power. So negative to the fourth power, remember, it's going to go from negative times negative, positive, times negative, negative, times negative again, it will turn positive. So this right here is 4x squared. We got negative x to the third power. So will that stay the same? We got negative times negative, positive, times negative again, we got negative x to the third. But then we multiply that with negative 5. So that's going to be positive 5x to the third. Are there any changes right here? Well, the equation doesn't look the same, right? Because this one has positive, this one, or negative. The original has a negative, this one has a positive. So it's not the same, so it's not even. But are all terms the opposite? This term right here is opposite, but not this. Those are the same. So this is actually neither. It's neither even or odd. And let's go ahead and go to the third one. We have f of negative x right here. We got 2 times negative x to the fifth power. All right, so let's see what we have here. Negative to the odd power. Well, if you need to go through it, let's go through it one by one. Negative times negative. That's like x squared. It's going to be positive. Negative, positive, negative. Okay? So what we actually have right here is negative x to the fifth. So if we simplify it, this is negative 2x to the fifth. I look at the original equation, it's positive. I look at the equation after I substitute f of x with negative x, and we only have one term, and it's opposite, right? This one's positive, this one's negative. So that tells me that this is an odd function. All right, so that pretty much sums up the part of 4.8 that we're going to worry about. You're going to have to do some graphing, and remember the even and odd behaviors, or sorry, the end behaviors of the function, understanding what the degree of the polynomial, if it's even or odd, what the end behaviors are, and then we have repeated solutions. If you have repeated solutions, then that tells you it's either that it will be intersecting or just touching the x-axis. As far as understanding where your maximum and minimum is, we're not going to worry too much about that because realistically, you're going to use a graphing calculator if you had to do stuff in the real world. So what I care about is, do you understand where the zeros are for each function? Can you tell me what the end behaviors are, and at least give you a general idea of where the function will go through the x-axis or just touch the x-axis? And that right there is section 4.8 for us.